Okay, so we're actually going to go back to some stuff that we skipped last time because we ran out of time. So if I can find that, we will do that. Here we go. So last time we talked about a variety of things. We talked about basically every kind of join under the sun. We talked about every kind of, well, most subqueries under the sun, but not all of them. And we talked about the coalesce function, which is part of this miscellaneous data management type thing that we need to cover in this class. But we only talked about how to handle null values, and that was basically it. So we talked about null values and coalesce for default values, for arithmetic, and so on and so forth. Use coalesce, don't use if null. That's not part of the standard. So where we left off was control flow. So many of you have already programmed in other languages before. Control flow refers to the if-else statement. Actually, more precisely, it refers to the switch statement in this particular context. So let's go through that. And this syntax is pretty ugly. But it is the SQL standard way to write an if-else. My SQL has an if, it is not part of the SQL standard, so don't use it. Use these case statements. All right, so let's get started. So we have two statements that we want to learn here. A case operator that works similar to a switch. So you test the column against an expression or a value, and if it evaluates the true, you replace the column with some other value. There's also this null if construct that's very, very simple, so we're going to cover it in one line. Basically, if the thing you pass the null if is true, replace it with the null. So we'll see an example of a student who's an undeclared major, and we're going to replace that undeclared major with null. So the null if will do that for us. Okay, so we have this beautiful little table containing, or we call it Bruin base, containing midterm scores. What we're going to do is we're going to use all of these operators to form a better formatted table than what we have now. So we'll create a human readable version of the level, the career, and the GPA column. Oh, and by the way, you need this on the homework. That's why I'm coming back to it. So the first form of the case statement checks the column against the constant. So we case on the column. So we do select whatever we're going to select. And then for one particular result, we use case, and then the name of the column we want to check. Now, in this particular version of the case statement, which it's called the simple case statement, we only check on equality. So we check whether or not the column equals one of these things. And if so, if it evaluates it true, we output something else in its place in the result set. So here, we look at level. When the level is UFR, we're going to write out freshman. If it's at USO, we're going to write out sophomore. And finally, if it doesn't match any of these, we fall through to the else, which is going to return unclassified. Now, one thing that's very important here is the end as. So you always have to end your case statements. That's a syntactic requirement. But this as is very important. You have to rename the result of that case statement to something else. If you don't, the name of the column is that case statement. And you don't want to have to write that in a subquery. Check in a subquery, have to rewrite that case statement as the column name. So just always give it a name. So are there any questions about what this does? This doesn't replace anything in the original data. It just swaps values in the output of the data. Okay. There's another form of the case statement. This time, instead of doing case column, we simply write case and then a bunch of when expressions. The when expression is some kind of Boolean expression that we test against what's in the specified column. So these can get really weird. Typically, we only focus on one column, or we're consistent. If we can use two columns, but we need to be consistent, basically, in our expressions. Otherwise, really weird things happen. So here, when the level is less than, and there's actually an error here, when level is less than or equal to USR, then we're going to print undergraduate in the output. When level is less than or equal to, GD2, which is a doctoral student advanced to candidacy, so this is 4, then we're going to return graduate, and if the level is CHN, that's the chancellor. And again, we end the case statement and we rename it as new career. But if none of these match, we go to the else, which is unknown. Now, The error here is that MySQL does something funky compared to Postgres and other more compliant systems. You cannot compare against a string when you're using an enum in MySQL. You have to use the index of the enum. So 4 was equal to USR, I believe, and 7 was equal to GD2, I think, in the schema that we originally proposed. So it's not incredibly, the enums are not incredibly useful in this case. So 2 different ways to write a select case statement. Both of them, you need to rename the output. So again, if you don't rename the output, this is the name of your column. And MySQL will truncate it, but it's still gonna look very ugly. It's total rubbish. We don't want it. Now, we're only gonna stick with the simple case of case statements where we use the case statement in a select. You can use it in an order by or a where, and I saw some people in the final last year do that. That's okay, you just have to know what you're doing, basically. There are valid use cases for that. If you want to convert something to some other value and do a where on that, but you don't want to return that in the output, that's okay, you can use it in a where. So you can use it in order by, if you want to do some kind of filtering, some kind of ordering on something other than the value of the column. It can appear, subqueries can appear, I guess subqueries involving this, I don't know. Exists, you can use when with exists. You can use it in the update set statement. And it can also be used for the pivot operation, which we'll talk about today. This one, that might be an error from another slide. Subqueries can appear. Oh, I see what I'm saying. Nuanced case. You can write a subquery in a case statement. Why you'd want to do that, I don't know. So any questions about the case statement? Use it, don't use if, use the case statement. Now, next we'll learn about casting types. This is also used in your homework. When you use cast, column name as new type. But the new type is very specific. It's not just any random type implemented in MySQL. It's only these types that are listed on the screen. So you can cast a binary and char, date, time and year, decimal, double real, float, JSON, and if you're going to cast an integer type, here you have to specify signed or unsigned for the integer. So here's an example that's probably going to be pretty relevant for your homework. Here I cast a GPA, which could be 3 point and then a bunch of like 20 digits. I want to cast it so it has 4 total digits. The first, the one before the decimal is always 1 digit. We don't have a 10.0 GPA. So we're going to cast it as a decimal 4 with 3 of those digits after the decimal point. So 3.792 instead of 3.7923185 or whatever. So we can use everything that we learned now it's broken up because we split it across lectures. We can use everything we've learned now to create a beautiful report of this Bruin base or midterm scores report. What do we do here? So instead of level being UFR, USO, UJR, I use the case statement or a case statement to replace it with the name of the level. So freshman, sophomore, junior, senior, master's student, doctoral student, a candidate, and chancellor. So that's gonna be one column, and it's called class level. So I'm simply replacing, I'm taking the value of level, and I'm gonna output it as something else called class level in the output. I no longer have a level in the class in the output. Next, I do something with the career. Here. I take the career that's currently in the table and I replace it with its appropriate value according to these Boolean expressions. So this is the second form of a case statement. So we have undergraduate, graduate, and chancellor, otherwise unknown, and we call it career. So the original column was called career, and the output we're also going to call it career, but with different values. Now we have a couple other interesting things going on here as well. We have null if. This takes the parameter, and if it equals the first parameter, and if it equals the second parameter, we replace it with null. So if a student's major is undeclared, we replace it with a null, and then we rename the result as major. So that's null if, kind of cool. Then, if a midterm score is null, we're gonna replace it with a 0. So what do we use for that? Coalesce. So coalesce midterm 0, the first non-null element, which in some cases is going to be 0. If the midterm though is not null, then we just get back the midterm score. And we rename that in the output to midterm score. We no longer have a midterm in the output, we have midterm score in the output. And then finally, we cast the GPA as a decimal for 3, and then rename it to GPA, which has the same name. From Bruin base ordered by student name. So this can get you may want to get used to this because you sometimes have to write stuff like this to make reports look nice. Up here, I didn't cover some of these functions this year, but what we did here is we took the last name, the first name, we took the last name, added a comma and a space, and the first name. If there's a middle initial, we then add a space in the middle initial. But if there's not a middle initial, we just end after the first name. So if you're wondering what that is, we convert it also to uppercase. So take a look at that, see if you can figure out what each part of that is doing. So are there any questions about this long query and what it does? And what it doesn't do? Yeah?
Can we remove the else if we don't have anything to give?
Yeah, if you're positive you're never going to hit the else statement, you can leave it out, but it's strongly recommended that you leave it in. You should never reach that case, basically. In some cases, in some implementations I've seen, the condition falls through. So if you don't have an else, you end up getting the last condition, even if it's not true. That becomes the else, essentially. It's weird, but I think in, I don't know if it's MySQL or Postgres, but in one of those two, that could happen in certain cases, especially with the second type of case statement. Anything else on all this? All right. So we get back this beautiful output that's concatenated the student name, replace their class level and career with the proper descriptors, replace an undeclared major with null, poor guy, midterm score, and then round it as GPA or cast it as a decimal. Okay, so that was lecture 3. That's finishing off lecture 3. Today we're going to go into lecture 4. And this lecture contains a lot of material. I'm actually going to either skip some of it or go quickly through some of it. I added some extra slides here to be complete with what the book does and what some other academics do for this material. It's stuff that I've rarely seen used in practice, but I'm putting it in to be complete, but we're going to skip over some of it or go through it relatively quickly. If my pace is fast, it means it's probably not all that important, but I still want you to be exposed to it. And of course, stop me if you have questions. So we're going to cover a lot of stuff today. The pivot, which usually I cover with OLAP, which is the last lecture, but I'm going to do it now since we just talked about the case statement. Set operations. This is going to involve a lot more of joins and subqueries that we haven't gotten to yet. Window functions, this is like really important. Common table expressions, CTEs, and recursive SQL, somewhat important. As somebody on Quora wrote, this only applies to probably 0.01% of queries that you would ever write. I've never written a recursive SQL query in my career. I don't know if many analysts have. I do know where it's useful. Actually, I take it back. I have. We'll talk about that when we get to there. And then processing text in JSON, which is actually a very quick section. So we get through what we get through, and I'll either ask you to read it if it's simple enough to understand from reading it, or we'll just skip it. So let's first talk about the pivot. The pivot is one of 5 what are called OLAP operations. Most of what we worked at in this class is called OLTP, or online transaction processing. You don't have to really remember that phrase for now. Basically what it means is that at all times during the day in this MySQL server, we're reading from the server, we're also writing to the server, and we're updating the data in the server. We're doing this all day long. It's constant reads and writes all throughout the day. This is what a production MySQL server might look like. But what a lot of analysts use, many will use OLTP. You'll read from a MySQL database. But some of you, many of you, all of you, are also going to work with what's called a data warehouse, which follows OLAP, the OLAP framework. OLAP stands for Online Analytical Processing. This data is not up to date. It's usually 1 day old, maybe 12 hours at the least. It's usually 1 day old, and that's okay for your job because you're not a software engineer. You're not trying to keep the site running and keep the data up to date. You're running reports about what happened the previous day, or the previous week, or the previous quarter. So all you need is a bunch of aggregate information. So OLAP we'll talk about next time if we have time. And there's 5 operations. There's slice, dice, roll up, drill down, and pivot. I'm only gonna cover pivot in this lecture. We will talk about the other 4 next time. The pivot operation takes data from long format and converts it to wide format. So on your last homework, you had a case where I asked you to report the total throughput for departures and arrivals. And given what you had known at the time, you could only summarize, you'd have 1 row for Terminal 1 international arrivals, 1 row Terminal 1 international departures, 1 row Terminal 1 domestic departures, and so on and so forth. But what you can do, and some of you try to do this too, which is good, you tried to pivot. So you reported the throughput like this. You had T1, T2, T3, and then you had 2 columns. You had departure and arrival. The data that you output, the data that you're working with is in the long format. So you have multiple rows per terminal, basically. What those students and what the pivot does is it turns the long format into the wide format. So now each object being a terminal is 1 row with multiple columns associated with that row. So let's look at an example here. Suppose I'm running Learn or Canvas, whatever we want to call it, and I report a bunch of homework scores, homework 1 through 5, with a UID and a name and whatever the score was that they got in their homework. This is called the long format. You see that each student is represented multiple times. We have Joe Schmo appears 3 times, 1 for each homework assignment that he turns in. This is good for a software engineering perspective for several reasons that we'll get to. But for you and a lot of analysts, you typically want like a spreadsheet view. And what I use, this is the instructor. We have 1 row per student and then multiple columns representing scores. So this is called the wide format. Okay, so we're going to represent this table 2 ways. This is the wide format, as I mentioned before. What's a problem with this format? Well, there's a lot of problems with this format. So, what do you think? Let's see. Let's go with the pluses first. What's a good thing about this format? Just shout it out. It's readable. That's about it. What's bad about this format? So 1 is that it's not flexible. If I decide I want to add a 5th homework assignment, I have to use an alter table, which if I had millions of students like Coursera does or whatever, that could take a long time. So it's not flexible. And there was one other thing I mentioned here. Oh, what's one other? We can have nulls, which are bad in theory and just take up space. So readability is the main thing that we're going at with the wide format. And here's the long format. What are some good things? So let's start with the negatives. What are some negatives about the long format? It's not as readable. What else? Yeah, there's a lot of redundant data. The same UID and name is repeated over and over again. What is a positive of this? What are a couple positives?
It's flexible, so you can constantly insert statements.
Yeah, so if I want to create no more homework assignments, it's flexible, I can do that. And the other is that there's no nulls. Software engineers typically prefer this format. And even as an analyst, I tend to store things in this format and then pivot as needed. So are there any questions about what this means, long versus wide? It's a common question I ask. Given a particular problem, how are you going to store the data? how are you gonna represent the data when you print it to the screen? So in some cases, you store the data in the wide format, some you store it in the long format. And in other cases, when you represent the data, you're probably gonna represent it in the wide format. It just depends on the use case. Nothing? Okay, cool. For those of you who have used R, what is this called? So if you use the tidyverse, it's a spread or gather. There's also something called melt. I think it's the opposite of a melt. I don't know why it's called that. Spread, gather, melt, a pivot, longer, and pivot wider. Others. So you're gonna do this at some point in this program. I can't find a list of required classes anywhere, but at some point there's an R class. Which one? Oh, you're taking it now. Okay, cool. Cool, so then we can have a little fun activity or slide in a bit. So how are we gonna convert the long format into the wide format? This is weird. So and I was hoping to do a demo of this, but we're gonna tackle it in 2 steps. First, for every row in the long format, I'm gonna create 5 columns. So I'm gonna repeat what's in the first 2 columns. So I'm gonna have a UID and a full name. And then I'm gonna create 5 columns. When I'm creating those 5 columns though, I need to know which one of those columns to fill in. So the first step is I create, I have UID 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm gonna create, we have a name, Joe. And then we have homework 1, 2, 3, 4, 5. In the long format, I'm going to look at which assignment that row refers to. If it refers to homework 1, I'm going to take what's in, let's do this. If the row refers to homework 1, I'm going to take the mark associated with it, which is 100, and put it into homework 1. If the assignment is homework 2, then I'm going to take the mark, which is 90 here, and put it into homework 2. Everything else is going to be null, basically. So I'm going to fill in one thing per row. So homework, this looks like a null, it's homework 1. So homework 1 is 100, null, 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 null. There's only 4 homeworks, whatever. So, and I'm going to keep doing this. So in this temporary output, I'm going to have another row, 1, 2, 3, 4, 5, 6, 7, 8, 9 for Joe. This time I'm going to fill in homework 2 because the second row here is for homework 2. So homework 1 is going to be null, homework 2 is going to be 90, and then the rest are null. And so on and so forth. Each student is still going to have a maximum of four rows associated with them, but only one of the columns is going to be filled in. Does that make sense? Okay, now I have to do something with that. This is kind of like the map phase and map reduce, but we won't go there. Then we're going to collapse these 5 rows. We're going to group them together, collapse them into one row containing all in scores, with possibly some nulls if somebody didn't fill in, didn't do the homework. So that's what we're going to do. Collapse these 5 rows into one row, 4 rows, by using a sum and a group by. So the first, do I have it? Okay. This is why I wanted to do a demo. So step 1 is writing this query here. So I'm going to have a select UID full name, case, assignment when homework 1, then mark, else 0, end. Okay, so here, I'll just cross this, let's do this. Get rid of this and get rid of this for now. So in step 1, we do this. We do a bunch of case statements, one for each homework assignment. I check if the assignment is equal to homework 1, if the string homework 1. If it is, then I put the mark associated with that into a new column called homework 1. A column called homework 1. Otherwise, I put a 0 there. Then I move to if the assignment is homework 2, then I take the mark that's in that row and put it into the homework 2 column, and the others are 0, and so on and so forth. So that's basically what I just drew up on the slide a minute ago. So we can use a case statement to do this. So are there any questions about what we did there before we move on to the last step? Okay, so the last step then is we aggregate. We add a group by. We're going to group by the student and their full name. We don't have to group by their full name because UID is already a key. But we're going to group these 5 rows together, each row containing only 1 score, and then we're going to sum over them. So I keep saying 5, I mean 4. So I'm going to have, if somebody has turned in homework 1, the first row will have a homework 1 score. The next 3 will be 0. For homework 2, the first value will be 0, homework 2 will have a score, and then homeworks 3 and 4 will have 0. We collapse over those, we sum over those columns, and we end up getting 1 row per student. And it looks like this. So we now end up, just summing up over those groups, and we get back the wide format. This is the wide format. So are there any questions? Yeah.
So actually, removing the sum and group by would give the same output, right? Just the case statement.
If you remove what?
Remove the sum and group by, just the first step and the second step. What's the difference? The output would have been same, right? After the first step and the second step.
No, the output, if you eliminate the group by and the sum, you get back this. You get back 4 or 5 rows per student. Just only one of the values is filled in for each row. Then once you do the group by and the sum, then you get this output. I sum across these columns. So 100 plus null, or in this case I use 0. So 100 plus 0, 0 plus 90. If I had a score here, it would be 0 plus 0 plus score, and so on. Any other questions on pivot?
Do we have a specific use case for using pivots?
Yeah, the specific use case is when you have data in a long format. So it's sometimes called in like SPSS or SAS and Stata, multiple records per observation. So here we had multiple records per student, 1 for each assignment. This is very, very, very common to see data in the long format. You're converting it into a nicer, easy to read format where each attribute associated with that student has its own column, so which is 4 homework scores. This is a very, very common operation in analytics. How do we convert from wide to long? This isn't as useful, so I'll tell you to look at the lecture SQL code. You have to make clever use of the union operator, which we'll actually talk about in this lecture. Okay, so that covers pivot and data management, essentially.
Can we do dynamic pivot table?
No, it's not part of the SQL standard. So you have to use a case statement in order to create a pivot table for this class. Each system, MySQL has a pivoting operator. Postgres has a pivoting function. None of those are in the standard though. Okay, set-like operations. Now we're going to talk about sets again. And we're going to talk about a couple of different join types. I'm going to skim, yeah.
Sorry, can you use max instead of sum? Like max case?
Yes, you can also use max, yeah. Assuming, because you have a bunch of zeros basically, yeah. But it won't work in some other cases. Mm-hmm. Yeah, max will work because you're comparing a score to a bunch of zeros. And if they're all 0, well, you still get a 0. Yeah. So these are not, a lot of these types of joins you write intuitively without really realizing you're writing these kinds of joins. So I'm going to go through them a little bit, but you'll have some practice on the homework with this. There's one problem where I ask you, there's 3 ways to write the query. And the bonus is you write one way, the bonus is you write the other 2 ways. So pay close attention. One is called the semijoin, and one is called the antijoin. These are just filtering operations. And the way that I'm going to teach it is using the original join notation, which is join, left join, inner join, or in exists and not in. Now, the semi-join and the anti-join are native in Hive and Spark, and I think Presto. So there's no syntax for a semi or anti-join in the SQL standard, but Hive does have one. They call it left semi-join or left anti-join. So here I have two tables. Like I said, this should look familiar. The format's not exactly the same, I don't think. We have a flight table and we have an aircraft table. We're going to filter the flight table using the aircraft table. And we can do that using a semi-join and an anti-join. So the semi-join is simply defined as essentially an inner join between R and S. I know it says natural join here. Theoretically, it's a natural join, but in SQL, it's always a theta join or an inner join in this particular case. We join the two tables together, and we only project out the columns in the left table, only the columns in R. This basically is a filter. It takes R, which is the left-hand table, and filters using the rows in S, which is the right-hand table. So what do? I have this flight table and I have this aircraft table, and I want to compute the semi-join, the left semi-join of flight and aircraft. Basically, it's saying I want to keep rows in SW flight that have a match in airtran. So which rows is that going to be? That is going to be I have these two guys here, and we see that they have a match here and here. So in this flight table, I only have two flights that use an aircraft that was owned by Airtran at one time. So the only rows that I get back are these two rows. These are the only two flights that use an Airtran aircraft. That is the left semi-join. But I only project out the columns that are in the left table. So in the right table, I also have a type and a full type. So in the inner join, I'll get back all of those columns. But in the left semi-join, I only get back the columns in the left table in R. So R and S. So I don't have type or full type in the result. This differs a little bit from the homework, but there's a reason for that. So are there any questions about what a semi-join does? Uh-huh.
How is it different than an inner join and a select statement?
So an inner join is going to give you back all the columns. If you use a select statement and you only project out the left side, then yes, that is a left semi-join, written as an inner join. Yeah. So there's three ways to write a left semi-join. One is to use the inner join. So I simply take the inner join between the two tables, but only project out what's on the left-hand side. So this is columns in L only. In some text, you're going to see select distinct L dot star. I'm trying to be consistent with the select star thing. Now, that's one way to write a left semi-join. The other way to write a left semi-join, and these are semi-join-like, we won't be pedantic about it, but they're more or less semi-joins. The other thing I can do is use the in subquery. So this is something new that we're learning today, which is I can use in and a subquery, and that creates a set of rows, set of values. I can then use the where clause to check that the tail is in this particular value, set of values from the subquery. This is equivalent to an on L.tail equals R.tail. So it's a pseudo join kind of using a subquery. So we've learned inner join, we've learned in. This one exists. This is the only formal definition of a semi-join. I hate this definition, and I think a lot of people do, because it uses this really weird syntax. What it's saying is select the left-hand side columns from flight, the flight table, where certain rows exist. The rows that have to exist are rows where the tail on the left-hand side and the tail on the right-hand side are equal. So it's kind of like a join. And we're going to check the tails are equal to each other. If they are, we're going to have a bunch of values in that subquery. The exists just means that that subquery returns at least one result. If the subquery is empty, it's an empty set, well then the whole thing's false. We don't include that row in the output. Now the select one, this is what confuses a lot of people, myself as well. This is just a convention. I think you can also use select 0. I don't know if select null works, but they just use select 1. It means give me something to indicate that there's a row there. So that's what the select 1 does. It just basically any value, maybe not null. This is the formal way of writing a left semi-join. What is wrong with the subquery? Or what do we think might be wrong with the subquery? Look at, here's a hint. It's what?
Correlated.
It's a correlated subquery. Now, this is an exception. For whatever reason, they decided to make this part of the standard, this correlated subquery. Because it's part of the standard, optimizers know how to efficiently process this correlated subquery. So it's actually very fast. It converts it into another form. I want to say it's a set containment form. I'm not positive there. Correlated, but it's optimized away because it is such an important construct in the standard. So correlated subqueries do have use, and they can be very efficient, assuming they're part of the standard and the database supports that operation. So any questions on select exists? Yeah.
In terms of processing across all the three ways of doing it, is there any difference?
There is a difference. Oh, I thought it was 2:45. All right. We need to take a break. There is a big difference. Where exists is the most efficient in database systems, even though it has a correlated subquery. In depends. This one's always the most efficient. The other two, it depends on a lot of things. And I really shouldn't even say always, but this is the most popular way. In most cases, this is the most efficient using exists. The other two, it depends on a variety of things.
Would we say the in is more readable or?
Yes. Yeah, so I absolutely, you can use this. You will not lose points for this because it's part of the standard. In and the inner join are absolutely more understandable to read. People like this though, and it is part of the standard. So if you like this, you can use this. It's perfectly fine. But because this is technically the definition of a semi-join. Right. Anything else?
Will this be slower?
Exist is not slower, no. Exist is usually going to be the fastest because the database optimizes for, it really likes exists for a semi-join, basically, because it's part of the standard, I guess. I wanted to say something else. Oh, aside from this weird one, the other two methods that if you use those, you don't even realize you're writing a semi-join, usually. Like, I don't even have to cover this. I am, because it's important, but I don't even have to cover this, and you could probably figure out what the other two do. Weird things happen if you have nulls on the left-hand side, so try not to have nulls on the left-hand side. It's implementation specific, but if you try to test null in a set containing a null, you don't get back true because you can't compare nulls. You get back unknown, which is basically false. So if you have a null on the left-hand side and you write a left semi-join, you're gonna lose that row. Little nuance. The anti-join is the exact opposite of the semi-join, so I won't go into the meaty details of this. Presumably, we only project out the attributes in R still. This is written in terms of the semi-join. The anti-join is the complete opposite. Given a table, find all rows in that table that do not exist in the other table. So given R, get me all rows in R that do not exist in S. So I don't have a graphic here. So all rows in R that are not in S. It's written with this little triangle, but basically the gist is you use, instead of in, you use not in. Instead of exists, use not exists, and so on. The only difference is the join part. Technically, they can both be written using the left join, including the left semi-join. And maybe that's why people use left join, because it's called left semi-join. But inner join can be, you can write an inner join as a left outer join. I suggest practicing that, because you're going to see that, and you should be able to recognize what's going on there. Here, though, we cannot use an inner join. We're going to use a left outer join. So we specify the columns that we're going to match against. We perform a standard left join, but we want to find rows in R that are not in S. So when we do the left join, we want to check that the columns that are supposed to be in S are null. And then we project out the columns that are in the left side. So we would write it like this. Select blah, which is the left-hand side only. From flight L, left outer join airtran aircraft R. Same join condition, L.tail equals R.tail, where R.tail is null. This is the difference between an inner join and the left outer join and the anti-join here. So here's one way to write a left anti-join. Are there any questions? The other two are up to you. You can do it. Why are there so many ways to do this? Some of it's performance. If you're a DBA or really get to understand MySQL really well, you'll know which method to use when. And there's a big decision tree of when you should use which method. That I don't use MySQL much, so I don't know it, but in Postgres I know it. One way may be easier to understand. So for example, in or the inner join may be easier to understand, but it may not be as efficient. Here we care more about readability. Exists, though, is the standard way to do it. Okay, now we're going to switch topics a little bit, still related to sets, but now we're going to talk about set operators in the relational algebra, and then we're going to talk about how to implement these set operators in SQL. So what we did before was set-like. They weren't exactly sets. Well, they are, but we didn't cover it that way. So when we do a set operation between two sets, the two sets have to be compatible, meaning they have to have the same number of attributes. Each attribute must be the same type, and so the domain must be the same, and the attribute names must be the same. Set union is defined as on the screen, and most of you probably already understand this. In R, understand what a set union is, at least in R, what is a set union equivalent to? If we treat a data frame as a set of rows, what is union equivalent to? R-bind, and I think in NumPy or Pandas it's stack. So you're taking a set of rows and you're appending another set of rows. Is everyone with me here? The union between two sets, What? What is it? Concat? Yeah, it's concat. Stack is something else. All right, so set union. If anyone doesn't understand this, please let me know. All right. So we have two sets here, two relations, undergrad students and grad students. We have a UID and a name and a GPA for both. Can I compute the union here?
Yes.
Yes, because both relations have a UID column that's of the same type. Both have a name attribute that has the same type, and both have a GPA column that has the same type. So yes, and what is the result? Well, it's going to be UID, name, and GPA. I won't fill in the rest, but we have Josie, Joe, Sarah, Joe, John, not Joe, Johnny, Tim, and Erica. And then we fill in their results as well. If there are any duplicates, I remove them. The union operator is is a relational algebra operator. What about these two? Can I take the union of these two?
No.
No, because these two columns do not have the same name. The other two attributes match, but I have two attributes that do not match, so I cannot do that here. So how would I do that? If I want to force it, how do I do it? Yeah, I rename. So I rename ugrad GPA to GPA and grad GPA to GPA. So we do this. We'll call this R and this S. This be S. Like that. So in the SQL standard, if you have two relations that you want to union together, and they don't have the same attribute names, but they have the same types, you have to rename the attribute that doesn't match. Oracle, somebody told me in Oracle, apparently it doesn't matter. It'll still do the union even if the attribute names don't match. But so different systems do this differently. But in the SQL standard, you would have to rename them. All right, any questions? All right. Set difference. Everything in R that isn't in S. So this is more or less review. Stuff you've learned before. You've learned what a set union is, an intersection. Okay, I'm just double checking. Not getting a lot of feedback here. So everything that's in R that isn't in S. Some of you are probably wondering why we're talking about this, and we'll get there. And then finally, R intersect S, everything in both. In R and S. So, Venn diagram is this here. This one is everything in R that is not in S. So that's this here. And the set union is going to be everything. So with Venn diagrams. Now, there is a point to this, I swear, but we have to introduce these operators first. This actually concludes our discussion of relational algebra. It's the last three operators we were going to talk about. Now, why did we learn about the relational algebra in general? You guys had a much better attitude this year about it than last year's group. So thank you for that. They found out apparently that it was useful, like I knew it was. So relational algebra helps us simplify discussion of more complex topics in relational data management that have to be precise. So mathematics is precise, relational algebra is precise. Words that are coming out of my mouth, though, are not necessarily precise, though I try. It provides a framework for understanding more complex operations like joins. We have a basic operator called the Cartesian product that lets us now understand how to do a join. We create all pairs first. You get flustered, all you do is you create all pairs first, and then apply a selection to it, and boom, you have a join. It's a universal language that's based on set theory that we can use not only for relational systems, database systems, but also relational layers. So Hive, Spark SQL, Pig. Pig is a scripting language that's based on relational algebra. They all use these operators. And they come up in pretty much any data management system that's tabular as well. And of course, it's also influenced non-relational databases. So you're learning R. Hopefully you're learning the tidyverse, which is an extension of R. And you can now understand, if you don't know what this does, you can write a relational algebra expression to show what it does. And more importantly, you can convert this into SQL if you understand the relational algebra. Instead of having to memorize, what is filter in SQL? It's where. What is select? Oh, it's select in SQL also. Convert everything so you have all of your packages. You got your SAS, you got your R, you got Mongo and everything, and you want to convert to SQL. Well, all you need to do is convert to the relational algebra first, and then easily write into SQL rather than having to do this. Memorize all the different ways of getting from SAS, R, and MongoDB to SQL. So how would we write this in relational algebra? Well, let's start with the first thing here. My relation R is adds. I'm going to filter the impressions attribute associated with that data frame. I only want impressions greater than 0. So that is a sigma operator. Then I do a group by because, well, the next operator is actually group by. A group by and a summarize. So I group by ID and AB. So ID is the add ID. AB represents whether this add appeared in the A part of the AB test or the B part of the AB test. That's it. So which operator is that? It's the group by operator, but how do I represent it in relational algebra? Yeah, so you need to review this. I won't test as heavily on it as I did last year, but you are still going to see it. So what goes to the left of this operator?
ID.
Yeah, ID and AB. And to the right is going to be average of imps, renamed to AVG imps, and average clicks, renamed to average clicks. Now here the mean is AVG, it's the same thing. Or it's as close as we can get. Then what? Then I have a select. What operator is that? Pi. So I select add, arrow add ID, group. Is that right? Oh yes, that's right. AB becomes group. You know, control versus experiment, and I don't even need. Oh, I do need to select average imps and average clicks.
Are we expected to know this during the exam?
Yes. Yes.
And do we, like, I mean, will we have pen and paper to write out all of these and then upload a photo with the
Well,
exam?
we can give you scratch paper. Yeah. It'll probably be something like, we're not gonna be able to, I don't know if we can use these symbols, but it might be something like you write gamma. We'll give you a grammar to do it. MongoDB, not relational, but we still use relational algebra to talk about it. When you do a query in MongoDB, you don't have to worry about this. We're not talking about MongoDB. The first part is it's called the selection or the sigma. It's the where. And the second part is actually called the projection. They use that term. So in my other class, a lot of times what I do is I give them a MongoDB schema and a query, and I tell them now convert it into either relational algebra, that's always a question, or convert it into SQL. Or I'll give them some SQL code and I'll tell them to convert it into MongoDB. As long as they understand the relational algebra underneath it, it's more or less straightforward to do. We won't do that in this class though. So we've talked about set-like operators, which are semijoins. We've talked about set operators in the relational algebra. Now we're going to talk about set operations in SQL. Now this section is going to go kind of quickly for a couple of reasons. It's not the most useful thing in this lecture or this class. And second, some of it's not even implemented in MySQL. It's part of the standard, but MySQL decided not to implement it. So here we go. Say I have this little, this is so nuanced that I have to create a little toy data set because you don't see this a whole lot in practice. It contains a name and a sport that the student plays. Now, I could have multiple tables if I want involved in these set operators, but they have to be compatible. So either I'm gonna have to have two tables that have name and sport, or I'm gonna have to have two tables that I can rename and select from in order to get two compatible sets. So so that's the catch here. The union and union all operators, of these three, this is probably the most important one, and it's probably the most simple SQL operator known to the universe. It simply takes two groups of rows and concatenates them. So let's say I want to find all students that play softball or soccer. And I don't want to use the where clause for some reason. So I just select the student name from student athletes where sport equals softball. And I select separately student names where sport equals soccer. And then I union them together. And I get the same result. Now, removes duplicates. Union removes duplicates because it's a relational algebra operator. So who plays soccer or football? Softball or soccer? That's going to be Sally, Sean, and Mark. Now, union all keeps all of the duplicates if you need them. We'll see an example of that later. Questions on union. All right, it's also used in the pivot. The intersect operator, here I'm going to speed up a little bit. This is not implemented in SQL, so we won't talk a whole lot about it. It's not in my SQL, but it's implemented in the standard. So in Postgres, this works. Now I want to find all students that play both football and soccer. Notice that I cannot do this with the where clause, because the where clause processes rows. I'm basically looking across, kind of pseudo comparing across columns now. I can't compare across, actually, let me take that back, reword it more precisely. When I'm doing a where clause, I can only look at one row at a time. I can't look at, say, Ryan football and then look ahead to see if there's any other Ryan rows with soccer in them. We can't do that at this point. So what we have to do is we have to use an intersect operator here. We select all students that play football. We select all students that play soccer. We're talking about American football here, so they're not equivalent. And here, this is S, R, and S simply returns a set of students and dedupes them that play both sports. But it does not work in MySQL. So the result is Sean and Mark. They both play football and soccer. Except is the set difference operator. Set difference operator. So here again, here I can write a where clause again, so it's a trivial example. But here I want to find all students that only play football. They play football and nothing else. So I could write this with the where clause, or I can use the except operator. So first I select all students that play football, and then I find all students that don't play football. They play something else. I complete R minus S. Everything in R that is not an S. Everybody that plays football but does not play any other sport. And there's an equivalent where clause as well. Again, not in MySQL. And I get back Ryan and Ben play football but nothing else. Okay. So any questions on union, intersections, and except? Okay. Next, we've already seen an in subquery and a not in subquery. We can also use in and not in with just scalar values. So let's say I want to find all aircraft that are a 737 or a 738 or 737-800 to be technical. I could write it using a where clause, or I can write it using a set containment, a set. So we're type in B737, B738. The set, this guy here is slower. Especially if you have a lot of values. Here it's probably not going to make a difference. But if you have a lot of values, that's going to be much slower. A join is faster. A semi-join using exists. So all of this is kind of melding together. And this is why I have preferences as to how I like to write queries. It's too overwhelming. There are too many ways to do the same thing in SQL. So try to stick to a few. Some people, though, develop very bad habits, or particularly in this class, they develop a habit of using one construct only and trying to shoehorn everything into that one construct. That's the unfortunate part where I have to take off points, because now I can't assess if you really know the full broad scope of SQL, or if you just know how to use this one concept. So it's okay to do things differently, but if you're always relying on the same thing, or you're doing something in a very esoteric way, that's not good. Similarly, I can test that a certain tail does not match any of these tails using a bunch of not equal to and ands, or I can use the not in subquery.
Professor, does this include nulls?
Nulls, right, nulls, if you use in, a null will be removed. If you use not in, the null will remain. So null in is removed. Null not in is kept. Now I had a slide last year, but it took way too long to go through. If you break down the set here and what it's doing, you rewrite. If you rewrite 2 here, like number 1, and then try to do that with nulls, you'll understand why it's the case. So just convert the not in to a bunch of not equal to's with ands, and you'll see why this is the case, why with the ins, nulls aren't filtered out and the not ins are not filtered out. Okay, so any questions about in and not in? Pretty important. But you shouldn't rely on them. You shouldn't rely on them if you have a lot of values to check. Now, another area where I'm going to,
I have a question.
yeah,
In the not-ins, do we usually use like discrete values or it can be an integer?
it can be both. So there's 2 different in and not in subqueries. One is just a set containment. This is just a raw literal set of values. The other, which is probably more useful, is, and it's actually more efficient, is to have a subquery. So you have results that form the set that you're checking in or not in. Yeah. Because the optimizer can optimize away the subquery. It can't optimize away a bunch of literal values. Any other questions on in and not in? Okay. These I'm going to glance over. A lot of academics really like these types of queries, the any, some, and all subqueries. I've never used one. There are some niche use cases for it, but they're a syntactic sugar for some other types of subqueries. So for example, you can write, if you're testing on equality and you use in, that's equivalent to using equals any and equals sum and putting a subquery into the any and the sum. So basically it's saying, does my value S1 match anything in that subquery? That's equivalent to saying, is my value in the results of the subquery? So for equals, in is equivalent to any and sum, but it's not always true. With a greater than or equal, less than or equal, and maybe even a not equal, this it has a different meaning. It doesn't mean in. This is checking that S1 is greater than all values, is greater than any value in the result of that subquery. In other words, is S1 not the minimum? Is S1 greater than anything in that subquery? So this is the only case where using any is absolutely required. I think you can do this with a window function though. If you want to check that a particular value doesn't match anything, you could use the not equal to any or not equal to sum. Any and sum are the same thing. Sum doesn't make any sense to me, but some people like it. So any is the same thing as sum. There's also the all subquery, where you're checking that S1 something, all the values in the subquery. So for example, if I want to check that S1 doesn't equal any of the values, so this any all is confusing. Basically, S1 does not equal value in select S2 from T2 for all S1 or all S2 in the subquery. We'll just write subhand there. So this is testing that for every value in that subquery, S1 does not equal it. In English, we would say S1 does not equal any of the values in that subquery. But any is a different kind of subquery. This is why I don't like teaching this subquery, because the language behind it is bizarre. This is equivalent to not in, folks. So just write not in. If you want to check that S1 doesn't equal any of the values in that subquery, use not in. But all does work. So we may actually finish. Is that possible to finish early? I'd be very shocked if we did. But some of this is just fluff that we can skip over. All right. That's all on all. Of course, this one makes a little bit more sense. We want to find values S1 such that S1 is greater than all the values, or every value in that subquery. Okay. So are there any questions? If we keep this up, then I'm going to go over part of the homework. Assuming I can get internet. My iPad should work.
Both of these any and all can be done in other ways, right? There would be no application where this is the only way to write a query.
There are some niche cases where it's the only way to write it. So generally use in or not in. These are the niche cases. This is one. This is a case where you want to see whether or not S1 comparator, in this case, is greater than any value in that subquery. There may be another way to do this.
We can take a min from the subquery and then.
Yeah, you can take a min. Yes, you can take a min. Yeah, so that's probably how I would write it. I don't use any sum and all subqueries. So yeah, you can write in a subquery, selecting the min of that table, and then checking that it's greater than that. So it's a scalar subquery. So here we can replace with, let's do that, can replace with a scalar subquery using min. And likewise, if we switch the sign to less than, then we can just use a scalar subquery with max. Nice job. All right, so that's one niche example. This is the other niche example. But you could find, I'm sure you could find another way to write this as well. This would be greater than the max, basically, in a scalar subquery. So you can rewrite it that way. Some people like to write it this way. I think this is not readable. But if you were to use it and you use it correctly, it's fine. The standard allows you to use all. So this is another niche. So really in SQL, there's not very many cases where you absolutely can't do something another way, unless it's very, very dirt simple. So going back to lecture 2, those are kind of dirt simple things. There's no other way to do things other than the way that we did them there. Even there, that's not true. Some of you found other ways to do some of those operations. But when you're talking about, group bys, wheres, not a whole lot of ways to do it that are fundamentally different. Once you get into joins and subqueries, oh boy, there's a lot. So we've talked a few hours now about joins. We've talked about inner and outer joins. We've talked about inner and non-equa joins. We've talked about self joins and theta joins. And the most common ones that we write are the inner equa, the left outer. The self non-equa, very important. It's bolded for a reason. And semi-joins for filtering. Now, again, with semi-joins and anti-joins, you typically don't know that you're doing them. Because they're pretty intuitive. We talked about the non-equa self-join having two main use cases. One of them is for walking a hierarchy or a graph. The other is when we want to compare rows to other rows that are near them. We've already talked about the first case. We did that using a self-join, obviously. That was the friendship network. Now we're going to talk about the second case. Typically, every row is analyzed independently. We may group rows using a group by, but we cannot do things like compare this row to the next 5 rows. There's no concept of that in standard SQL because SQL is based on sets. So in the standard SQL, we can't do that. But we can do that using a self non-equal join, or what we're going to talk about today. So by the end of this lecture, you're going to be sick of hearing about self non-equal joins. So this is a real example. It's the most complicated query I've ever had to write. And this was at Riot. We were trying to build a fraud detection system. And many of the features of the system involved counting transactions that were chargebacks. So somebody's kid gets a hold of their credit card, they try to buy a bunch of skins or whatever, and mom and dad find out, and they call their credit card company to dispute the charge. They say the child did not have authorization to use my card. What happens then is the credit card company or the bank issues a chargeback. They get their money back, and I don't know if Riot or whatever company it is returns the money, or if it's just a ding against their credit. So what happens is that when you're a marketplace that's scanning credit cards, if you get too many of these chargebacks, they cut you off, and you can no longer process a Visa card or a MasterCard or Discover or whatever. So you really want to avoid that. Other things can happen too. I think the gateway charge can increase, like as an insurance. Insurance can also go up for things like this. So it's very important that we minimize chargebacks and be able to predict when a charge is going to result in a chargeback. One way to do this is simply by looking at, has this person incurred a chargeback in the past? Now, typically, we just ban anybody that has a chargeback. They're doing something fraudulent, they stole somebody's card, we don't want their business. With a company like Riot, though, it's a little bit different because you have a lot of people that are underage or that don't have credit cards themselves. And my guess is they want to be a little bit more lenient, but not too lenient. Like, it's okay if the kid uses the card once and there's a chargeback. But we keep going too much or too many in too short of a time, then we cut them off and we don't let them buy anything anymore. So we're going to count the number of chargebacks up to and including a particular transaction of interest. So I charge something today. I'm going to look back 5 days and count how many of the transactions in those 5 days were also chargebacks. And we're going to do this at every transaction. So I'm comparing rows. So each row in this table basically says, transaction ID 1 was made by customer 1 at 2:15 a.m. on August 15th, 2012. It was for $1.50 and it was successful. So there's a 0 there. There was no chargeback filed. Write a query that computes for each transaction the number of cumulative chargebacks each customer had incurred in the previous 10 days. By transaction date, most recent at the top. So let's get into that and how we're going to approach this problem. We'll call this R. The strategy is very simple to what I taught you last time. This predates the strategy that I wrote up, by the way, so it's a little different. First, oh goodness, I have no idea how to solve this problem. Relax, it's a Cartesian product. That's what I always have to tell myself when I get flustered. First, we construct all pairs of tuples. Again, we rename one of them to L. And then I identify the join condition. So that was step 2. There's an equijoin condition and a non-equijoin condition. The equijoin condition allows us to eliminate rows that we know we don't want to join together. So when we're looking at chargebacks, we treat each customer independently. As customer 1, Riot doesn't care what customer 2 is doing. So we're going to join, the equijoin condition is going to be L.customer ID equals R.customer ID. Next, we're going to identify the non-equijoin conditions. And remember, these are always tricky. These 4 and 5 actually go with 3. I just couldn't figure out how to embed the bullet point. So for each row in L, we want to match to rows in R such that the difference between the dates is less than or equal to 10, basically. But we only want to do this on one side, meaning if I write the join condition incorrectly, I may join one row to another row that's after the first row or before the first row. So less than or equal to 10 also includes -5, for example. So what do we do there? We only restrict to one side. So we're going to restrict to where the right-hand side timestamp is less than or equal to the left-hand side timestamp. Otherwise, I also get rows that are after the timestamp that I'm analyzing. So that's a join condition. Then we look at what we want to return to the user. And that is simply the cumulative number of chargebacks, so a sum for each transaction. And then we order by the transaction time. So are there any questions about the steps about how we're going to tackle this? Okay. Here's how I would write the query. It's a self-join with an equijoin condition and a non-equijoin condition. So here, I'm checking that the distance between two dates is 10 days, including today. So today and the last 9 days forms 10 days. That's what the +1 is for. The less than or equal to, make sure that I'm including the current day. And then finally, I check, this is the tricky one, that the right-hand side time is less than or equal to the left-hand side time. So I'm looking at today and everything before it. If I don't include that, I'm looking at today, everything before it, and everything after it as well. Finally, I group by transaction ID and customer ID. I don't really need to group by customer ID if I have the transaction ID. And then I order by the transaction ID. Actually, I think I chose time here, which is correlated with the ID. So any questions on that self non-equijoin? Okay. So would this be 16? I'm sorry?
Is the date name going to return the absolute value? Like, why do we need to find it?
You could use the absolute, you cannot use the absolute value because that's going to look at, if I compare two dates, I may have a 10 or a -10.
I was like confused because like the sign will be already included in the date diff, right?
Yes, but there's a catch there though. It's possible checking less than or equal to 10 gives me less than or equal to 10, but also less than 0. So all values less than or equal to 10, which can also be negative. So even if I take the absolute value, I'm now going to get things that are in the future, essentially. So you have to be careful there. Yeah. So this will be the output of the self-join, the self-non-equijoin. So at the time of transaction ID 10, which is made by customer 2 had incurred 1 chargeback in the previous 10 days, including today's transaction. So this is called a sliding window or a moving window. So I know we're talking about MySQL here, but Postgres has a really good description of what a window function is. So it performs a calculation across a set of table rows that are somehow related to the current row within some window. It's similar to an aggregate function, but it tends to be cumulative, and it tends to compute an aggregation over a particular neighborhood of rows. So it sounds a lot like what we just did. Now, window functions were not always supported in MySQL. They were implemented in MySQL 8, which is the most recent version. Now, MySQL used to be numbers starting with 5, so 5.2, 5.5, 5.8. 5.8 is such a major improvement that they've split out the versioning, and now it's called version 8 instead. It's kind of like what OS 10 did a little bit on Mac. So you'll see 5.8 and 8 used interchangeably. 5.8 added a lot of SQL standard stuff that wasn't present previously, whereas Postgres has had it for years. Now, window functions were done with relational algebra. There is no equivalent to relational algebra. There is, though, with the tuple relational calculus, which we're not talking about. So we can rewrite that self non-equijoin as a standard SQL query, as a window function. Still a standard SQL query. We do that as follows. I select out the metadata that I'm interested in, which is trans ID and customer ID. Then I'm gonna compute a rolling sum, a sum over a window. So a sum of transactions within 10 days, or 10 days prior. So sum looks familiar, but it acts differently here because I'm specifying a window. In particular, I'm specifying a window with a order by. Now I'm specifying what the window is here. I'm gonna compute this rolling sum over days 10, which is a window, and I define the window down here. This window consists of 3 different parts. Not all of them are necessary. The first thing I do is I name the window, days 10. Then I have a partition by statement. The partition, what do you think we're not there yet. The partition by statement partitions things into independent groups where we do not care. If a row is in one partition, we do not care about any of the rows in any of the other partitions. So in terms of this transaction stuff, what am I gonna partition by? Well, it's up there. Customer ID, because I don't care, one customer doesn't matter versus one other customer in the aggregation. So this partition by is going to create a bunch of, partitions for customer 1, customer 2, and customer N. Okay. Then we have a bunch of rows, say 1, 2, 3, 4, 5, so on and so forth. The order by specifies how I order the rows within each partition. So I order by some particular column. Here it's a transaction time, because I want to compute this rolling average over time. So I have to have some kind of ordering there. So I order by trans time. So that's 1, 2, 3, 4, 5. Great. Once I've added an order by, this automatically becomes a rolling aggregate. It is no longer a grouping aggregate like we've learned before. So finally, I specify the neighborhood. The neighborhood, which is given by this third thing, is called a framing clause, you don't always have to use it, and in some cases you can't use it. I'm going to specify within each partition, given a row, what is the neighborhood around it. So let's say I'm looking at this row here, 4, and I want to compute for the previous 2 days. I'm constructing a frame where my pointer points at 4, but I'm only using 3 and 2, the 2 rows before it. This gets very complicated, we'll go through some of that. Finally, after I've computed this rolling sum, I then order the results by transaction ID. There's 2 different order by here. The first order by is within each partition. The outermost order by orders the results from the SQL query. 2 different uses. Any questions so far? Yeah.
Why do we need the order by inside the partition?
Because I need to order the values within each partition. This is a time series, basically. It's a time-ordered series of values, so I have to order with the rows within each partition in time order. Now, if I have space or something, or distance, I can order by distance. But there's some order to the rows. And I need to use distance of order in order to compute the window function.
Yeah, is it not possible to partition right where you do the over without specifying the window?
Without specifying what?
Like without specifying a window separately? Is it
Yes,
not
there is
possible?
another way to do it that I'll show in a minute.
So for the range part of it, how does the query know which variable has to be used for 9 days preceding and current row?
Yeah, so this is going to be based on the column, is based on the order by column, or columns. It's based on the order by. So if I order by trans time, the range, the frame specification is going to use trans time.
And if in a scenario there are multiple attributes in order by,
Yes.
it will just use the first one?
If you have multiple, that's a good question. I'm not sure how it would handle multiple in an order by. It may not be possible. You can partition by multiple. I'm not sure if you can order by multiple, but if I can find a use case, I can look that up. I've only used it with one. Yeah. Yeah, because then it becomes ambiguous what the framing specification is for. Anything else? I'm sorry?
Should it be a semicolon instead of descending? Constant.
Hmm. That's a good question. This matches a self-non-echo join, but I'm wondering if that's by chance. Let me look into that. Because my gut says it should be ascending order. And then, yeah, so 1, 2, 3, 4, 5. I'll look into that though. It might be a lucky, you might be right, and it might just be a lucky coincidence that I got the same result. Okay, we'll go through this individually as well. So if I run this window function, I get the same result. What's going on? Thank you. So we see that the result ends up being the same. So what on earth? What on earth does this window query do? We'll go into the individual parts now. I went through it in one slide, but we need more in order to do that. So let's first focus on the window itself. SQL is supposed to be very declarative, so it really shines here in the window function. So each partition is independent of any other. All customers are independent, so we partition by them. We don't care about customer 1 versus customer 2. We're only looking at each customer individually. Next, I have to order by something in each partition. This is usually time, something that has a distance metric associated with it. So we order by time. Now, within each partition, we can also specify a neighborhood around a row. This neighborhood is called a frame. So we have frames, we have windows, and we have partitions, which can get a little bit tricky to deal with here. Each frame in a partition contains the current row as well as rows around it that we have to specify. So in this case, we're looking at rows from 9 days ago, including today. This clause is actually optional. If we don't include the order by though, we end up getting something very similar to just a group by aggregation. Now, somebody asked, is there another way to do this? Yes, you can specify the window in line with the aggregation function. You can specify multiple windows if you want, and here's one way you do it. You can specify multiple aggregations, and each one can use a different window, or you can specify that they all use the same window, essentially, if you want. Both use cases are valid. So again, should I draw a picture again of what this partition stuff looks like? Yeah. So here's a partition. We'll call it partition 1 for customer 1. Let's say I have 5 a.m., 6 a.m., let's use dates. I have September 1, September 2, 3, 4, 5, 6. Let's say I'm interested in computing, let's say today is, I'm doing analysis for 9/3. Let's say I'm interested in computing today and the previous day. So I have a sum of chargebacks for today and the previous day. I'm going to construct a window or a frame and take the sum over that frame. Now, when I'm done analyzing 9/3, I'm then gonna report a sum for 9/3. Then I move the frame forward. Now I'm studying 9/4. I'm gonna compute a sum for the data for 9/3 and 9/4, and that's gonna become my output for 9/4, and so on and so forth. So you see what I did with the sliding window here? Cool. Now these windows can get more these frames can get more complex. So when we write a window function, we focus on 3 things: partitioning, ordering, and framing. So now we'll talk about the framing specification. There's a variety of ways to specify the frame. One is to use rows, numbers of rows around a particular row, or one is to use a range of time or distance around a particular row. So this is very, very convenient for us. So we can write, this is the syntax and how you write in various different kinds of frame specifications. If I want all rows before this one, excluding this row, I would use rows unbounded preceding as the frame specification. And in set theory, I guess, or in interval notation, it would look like the following. So all rows preceding this one. So starting at row 0 to the current row exclusive. So T we'll call the current row. N is the total rows. All rows after this one, excluding this one. That's rows unbounded following. So T to N. If I want to include the current row, I just add and current row. So rows between unbounded preceding and current row. That's going to be 0 to T inclusive. M rows before this one and N rows after. That's a rows between 2 preceding and 1 following. So that's going to be a T minus 2 and to T plus 1. We have to include the current row in that specification. And so on and so forth. So there's another, is there any other interesting ones here? So this one here, rows between 5 preceding and 5 following. So that's just T minus 5, T plus 5. Or we can specify a custom neighborhood. So rows, using a rows frame specifier specifies how many rows around a particular row I need to look to create my neighborhood. Before, after, or anything in between. So are there any questions about this syntax? This is something that you're going to have to use as a reference probably. You're not going to memorize it. I want to make sure you're with me here. How are we doing? Doing okay? It's syntax heavy, I know. Do we understand when to use, what the difference between a window function and an aggregation function is? Okay, cool. So we're that far. That's good. And we understand partitioning, ordering, and now we're on this. So this is the hardest part. You're going to have to have a cheat sheet, or you have your notes from Brew and Learn on the final for this. You're not going to memorize it. So that's rows. Now, for this particular problem, we're not interested in number of rows around things. We're interested in a time range. So if I have like a time series, even if I have a time series, as long as the delta between each data point is fixed, I can use rows. But if it's not fixed, like in real life, like transaction times, I have to use something else. I have to use the range specifier instead. How do I do that? Again, something you're not going to memorize, but something that's worth having in the notes that we post. Range interval, 5 days preceding. It takes the current row and looks and creates a neighborhood of all rows that are within 5 days preceding that row. Day can be month, minute, year, second, a variety of things. I can also use following here if I want to look into the future. I can also use minutes and seconds. This is supported in MySQL. I can look at intervals of 10 days preceding and current row. So you see that and current row coming up again, which is 11 days total. So are there any questions on the frame specification? All right. We'll move on to the last part, which is the actual window function. We had the window specification, now we have the window function. Now, we've learned about aggregate functions. A lot of aggregate functions are overloaded. That can also be used for, what is so funny? I'm sorry, I'm happy to have a good time here, but it's getting a bit distracting. And this is very, very hairy content. All right, so we've talked about aggregate functions, things like average, count, sum, min, max, things like that. And on a group by, we know how those work. Some of them are overloaded though to also work in a rolling fashion as well. So, but it depends on whether or not the window contains an order by. If the window contains an order by, that changes how these aggregate functions work. They become more rolling statistics. If we don't have the order by though, it ends up being similar to just a standard group by aggregate. So somebody asked last time about when we were doing, we joined the table together and we computed the z-scores individually for the undergrads and the grads. Somebody said, can we use a window function for that? Yes, we can, and the partition by helps us do that more easily. So those are aggregate functions. We also have non-aggregate functions. These non-aggregate functions tend to be simply position-based. So within a frame, so a neighborhood of rows, I can find what the first value in the frame is, what the last value of the frame is, and what the nth value of the frame is. So again, if I have a partition here, 1, 2, 3, 4, 5, and my frame looks like this. Let's say I'm currently indexed on 3. That's the row that I'm looking at. The first value in the frame is 1. So the output for row 2 is going to be 1 if I use first value. So first value using this frame for 3 returns 1. Last value will return 4, and I can also specify any value in between. So that's frame specific. Now, some functions are partition specific. These ones do not use a neighborhood. They use the full partition. These tend to be, these are more similar to aggregates, but they still work in a rolling fashion. So I won't go through all of these, I'll just mention some of them. We can rank rows within a partition if we have some order by. We can give a dense rank. So the difference here is just how ties are handled. We can compute a percentile within a partition as long as we have an order by. We can assign a row number. We can compute an intile, a percentile, a quintile, a decile. Actually, an intile, the n specifies what kind of tile you want. So 100 is going to be percentile, 10 will be decile, etc. Yeah, these you just can't. Well, in your next homework, you'll see examples of these. All right, we're going to get started again. We're going to get started again. I'll just wait. Thank you. All right, so there's a couple other functions that we need to cover that are very important for statistics. So we've talked about aggregation functions. We've talked about rolling functions. There's a couple that are really important for time series analysis. These are the lag and lead functions. So given a particular row within a particular frame, we can look at the previous row, the previous two rows prior to this one, or we can look at the next row or 2 rows following this one, whatever we want to do. This is very, very common in time series analysis. For example, in an autoaggressive, have you done any time series yet? No. Okay, so this might be a little new. In an autoaggressive time series, for example, and if I'm remembering my notation correctly, it might be something like you have some weight times the previous time point times some other weight times the previous time point, this two lags ago, times blah, blah, blah. So what's happening right now, the temperature right now, is basically predicted from the previous temperatures. And how many predictions in the past we look, you find by looking at an autocorrelation function or something. So we won't talk about that here, but a lag is basically the number of rows before a row, so, or a number of observations before this observation. So for x sub t minus 2 is 2 lags ago, or 2 values ago, 2 time periods ago. It's the same thing with rows. Given the current row, I want to look maybe 2 rows ago, or 1 row ago, and so on and so forth. The lag and lead functions allow you to do that. The lag function returns the value that is in rows before the current row, and returns that as the value for the current row. So at time x sub t, if I apply the lag function, the value that's going to get returned for x sub t in the output is going to be x sub t minus 2, if I use 2 lags. So in the output, if x sub t is the value that I'm observing, I'm going to return x sub t minus 2. So 2 rows prior to this row, and so on and so forth. So this is important for removing non-stationarity in a time series. And I have an example using a time series that we'll probably come back to. I don't know if we'll get to it, but I've given you the solutions to the exercises. Now, so since some functions only work on partitions, meaning they work on all of the data within a partition, there's no neighborhood involved. Since some functions only work on partitions, does that mean I still need to specify a frame or a neighborhood in the window function? And the answer is no, and in the SQL standard, the answer is you can't. So if you're only using functions that only apply to partitions, you cannot also specify a framing specification. So no neighborhood, no rows or range. So MySQL lets you do it, but it is not the equivalent to the standard. Now, okay. Now, this query is a snake in the grass. It's an aggregation or in a window function that is a bit nuanced. I have my UID, my last name, my first initial, and then I have 2 different aggregations. The first aggregation has no order by. What this is going to do is it's going to compute the average midterm in a rolling fashion over the entire partition. There is no neighborhood involved in this aggregation. Actually, I take that back. This is the one. In this one, we're going to have a rolling average over the entire partition. In the first window function, we have no order by. So we can't really do anything rolling because we have no order in the partition. So all this first aggregation returns is the aggregate that we learned in lecture 2. The aggregate we learned in lecture 2, but it's going to be repeated for each repetition of that second average too. So I'm going to have multiple copies of the group average over and over and over again. So this is the result that we get. As we see, we have repeated means over and over and over again, and we also have a rolling mean for each partition. Okay, are there any questions on window functions? Okay. I'm going to skip the examples for now and go on to the next topic, which is common table expressions and recursive SQL. So going back to the non-equal self-join, we've talked about window functions where we're looking at comparing a row to the rows before it or the rows after it, or some combination of the two. This time, we're going to go back to the problem where we try to navigate a hierarchy, a graph, or a tree. So in such a way that we don't have to write a nasty self non-equal join. Now, one query that I've written one time is I had to identify all launch analyses. So when when a Googler wants to launch, an engineer wants to launch some new algorithm, they will do a bunch of launch analyses to determine whether or not the launch is valid to go, whether or not the metrics look good on it. And what I had to find is I had to find all sets of experiments that were associated with a particular set of teams. And in order to find those teams, I need to identify who the people are. So each experiment is indexed by the username of the person that ran the experiment. So if I want all of the people that ran an experiment associated with related questions or something, I have to determine, is this person part of the related questions team? And in order to do that, I had to write a bunch of joins and basically write a bunch of self-non-equi joins to go up the stack, up the hierarchy, to find out which director they reported to. If the director they reported to was associated with the project that I was interested in, then I know to classify that launch as with a particular product. And so I could do that easily using a recursive SQL query, which is what I did instead of using a self-non-equi join. So we saw earlier, but to get FOF, friend of a friend, I simply do a self-join between two tables, a self-non-equi join, and I get back the FOFs of a particular user, of all the users that I care about here. Going one hop out isn't too difficult. Let's say now I want to find the FOF, friend of a friend of a friend. How do I do that? Well, this is the result. This is the query that I would write to do that. I'm not going to go through it, but you see that it's very, very messy. Going out one hop, it's easy to see if I have a cycle going on. Going out two hops, I now have to check if there's a cycle at the one hop computation and a cycle at the two hop computation. So there's a lot going on here that we don't need to get into. And then if I go out to 3 levels, it gets even worse. So how do I prevent this from happening? This is UG. So how do we go further than FOF? The query gets even more complicated. Instead, what we can write is we can write a recursive SQL statement. So in other programming languages, you've probably written some recursion and wondering where you were ever going to use recursion. Here, unfortunately, is one situation where you can't do it any other way. Languages that are so-called logic or declarative, like SQL, require the use of recursion over iteration. We can't iterate in SQL. Some new systems like DuckDB, for example, do mix a procedural language with SQL, so SQL can iterate and do cool things. But in most systems, it's declarative. What we can do is we can use a common table expression, or a CTE, in particular, a recursive common table expression. I'm behind here. All right. Now, a common table expression is not limited to recursive SQL, but it's usually introduced in recursive SQL. Common table expressions can actually be used to replace subqueries. So in my rules, I specify try not to use CTEs. I'm not gonna grade down for it, but you need to show me that you know how to use a subquery at least on an exam or the homework. Proponents argue that it's more readable to use a CTE. I don't agree with that because now the query is no longer linear. You now have to read the CTE first and say, oh, it actually goes in here. And it's kind of a nonlinear way of looking at the query. So for me, it's not as readable. CTEs, though, can be more efficient than using a subquery. For the subqueries we've written in this class, they're so simple that a subquery works fine. But as a subquery gets really complicated, a CTE is better. So let's stick to the guideline, though I won't enforce it a whole lot, that CTE should only be used for recursive SQL or when you're referring to the same SQL subquery over and over again. Here's an example of what a CTE looks like. That has nothing to do with recursion. I use the with statement, so with order values. So I'm creating a virtual table. It's not a temporary table, but it is ephemeral. With ordered value as, and then a query, essentially a subquery. That takes the result of that query and calls it order values. Then I have another query that I rename to and that I store as expensive products. Then finally, I write my final outermost query. and I reference the CTEs in the from and join clause. So basically, all you do is you take this and put it here, and this one gets put here. That's it. It's just a puzzle piece, essentially. You can just plug it in. So we can do recursive SQL using a CTE. We have to use a CTE because it's code that references itself. Good use for a CTE. So let's compute the factorial function. So the first thing we're going to do is we're going to define a CTE with width. It's a special CTE. It's a recursive CTE. And I'm going to call the CTE temp, for lack of a better name. These parameters here are things that we're going to keep in mind as we go through the recursion. So we'll call them memorized. It's memory. Each CTE for recursion follows the same flavor. There's a base case. This is what we start with, the data we start with to start the recursion. There's a recursive step that keeps the recursion going, produces more data, and then there's a termination step. In this case, the base case is 0, 1. I'm creating a little result set that looks like this. In and pres that contains the value 0 and 1. We're going to put 0 now where in is, and 1 where pres is. It's basically a variable. Next, I'm going to do a union all. This means I'm going to take this current result and add another result to it, concatenate it. I do that by creating a new result set. Select in plus 1 instead of in. So this increments the hop number. So we need to keep track of how many hops we're doing or how many numbers we're essentially computing here. So in plus 1 is, well, 1. And I need a new value for pres, which is in plus 1 times pres. Pres is 1, in plus 1 is 1, 1 times 1 is 1. The where clause doesn't fire. So now I go back to the beginning after the union all. I now select in plus 1 again, which is now 2. And I have 2 times pres, which is 2 times 1, which is 2. In is still not equal to 9, so I go back and I continue. In is now equal to 3, which is in plus 1. In is 2, so now it's 3. And in plus 1 times pres is going to be 3 times 2, which is 6. Now we keep going until we get to n equals 9. So we get 8 and 7, or 8 times 7 factorial, whatever that is. And once n is 9, we stop. We terminate the recursion. Now, I have all my results in the CTE. I need to actually get the results down. How do I do that? I do a select in pres from temp. That's it. This gets me all of the results. This is temp. It gets me all of the results. If I want a particular value, say the greatest value, which would be 8, then I say select in pres from temp where n equals 8. So any questions on the general form of a recursive SQL query? Yeah.
I did not understand how, like with the union all, when you do the other select inside from temp, that temp I'm assuming would also have 0, 1 and
It already has 0 and 1 in it,
so
yeah.
when you do union all, won't the result have many 0, 1 rows?
Well, one way to solve that is just get rid of the all. But we have to take it from somewhere. So we have to take the table from somewhere. And we take it from itself, basically. So we execute the query against the CTE, which is named temp. So you're right, we may get duplicates. That's why usually union all may or may not work there. That's why we usually put distinct here. And in future examples, I put distinct. If you try as is, though, it should work.
So, in the second select statement, the n plus 1, is the n thinking it's 0 or the 1 in the first select?
So after the base case, when we do select n plus 1, n is still equal to 0. But once we've selected the value in n plus 1, it becomes n. So the select statement here takes this and makes it n, and takes this and turns it into pres.
And it knows that it needs to do that because we are selecting it from 10.
It knows we need to do that because we defined a recursive CTE. If we didn't define it as recursive, then we don't know what we're doing. The database won't know what it's doing, essentially. But because recursive, it knows that doing a query from itself is expected. Anything else?
Do you have to have the n press?
The n plus, the pres.
The value in the parentheses?
Yes, you have to have n plus 1 times pres.
No. When you define the recursive, that parenthesis, the first parenthesis, the n comma press.
Oh, that's telling this CTE essentially how we're going to refer to our status variables. I have a status variable called n that I'm going to update and a status variable called pres. You can name it whatever you want. And actually, maybe this is a case where it's better to use different names. And I do show an example of that. But you can name it whatever you want. It's just the variable that we're going to use to track our status. And we can then reference it in the query.
So if I don't put it in there, would you'll be able to recognize it in the layer?
No, you have to specify it up there. That's just by definition of the recursive CTE. Let's look at another example. So here it is written in writing if you need it. It's basically what I explained. What do you think happens though if I remove the where clause? This where clause. Yeah, it's more nuanced than an infinite loop. We get overflow of the data type for n. So I don't know what data type MySQL is going to choose for n, but if it's say int and you infinitely recurse, you're going to end up blowing up that data type. So yeah, it's more nuanced than an infinite loop, but it's basically an infinite loop. Mm-hmm.
Technically, it will overflow first for pres, right?
I'm sorry?
Technically, it will first overflow for pres. Because
Yeah, pres will probably, and pres. Yeah, pres will overflow first because it's bigger. Yeah, pres will overflow way earlier than n.
If for the where clause you had like pres is less than 9, and then would it stop before pres becomes 9, or stop at the last time pres gets above?
It'll stop it will not execute. It's going to use the current value of pres to determine that. It won't use the next value. Yeah. Okay, so how can we explore the friends graph? And let me go through the wording here a little bit more carefully rather than just showing an example. So first we need to specify the columns that we are working with. But we need a status variable. We need to know where we are in the recursion. We're going to call this variable hops. So I start at hop 1, I believe, and we want to stop once we hit a certain number of hops, a certain distance. And we need to propagate this variable. So in order to do that, we use it in the select. We add hops plus 1 when we call our select statement. We need a base case, we need a termination condition, and we need a query to return the results from the CTE. So here's how I would write a recursive SQL queries for the friend of a friend example. On the exam last year, I didn't ask anybody to write a full recursive query. I think it was a fill in the blank or something. So I might do that for window functions too, I'm not sure. All right, so I'm going to have 3 variables that I'm going to propagate here. The number of hops, the user ID, and the friend user ID. Now here I'm using, I'm just using, I guess, acronyms here. Because it runs. My base case is here. I need to get data from somewhere. This is just the friends graph. So-and-so is friends with so-and-so. Then I have a union all. And this guy here is the recursive step. I take that table, the original table,
Can you make it larger?
yeah. I take that table and I join it with another table. That table is going to contain the same information that we did in our self non-equid join, but I also have hops plus 1. And I call it, rename it to hops. So now, after I join these two tables together, I'm at hop 2. I'm now at friends of a friend of a friend. I have my where condition, which is the same as before. It's a little bit different here. I have to do a not in because I need to make sure that I don't have any cycles when I'm creating the friends of a friend relationship or friend of a friend of a friend relationship. My termination condition is here. So I want hops to be less than or equal to 2. Once hops is greater than 2, we terminate the whole algorithm. We stop. The where clause is false, and we stop. We bail out of the recursion. Now, this is going to give me all results. It's going to give me friends, friend of a friend, friend of a friend of a friend, and so on and so forth. In order to get just the friend of a friend of a friend, I have to specify that I want the data associated with hops equal to 3. Also, I'm going to have many duplicates, maybe because of cycles or some other weirdness. So I do a select distinct. Mm-hmm.
I know for this case, I believe you defined that everyone has a friend. But if you were implementing this in a real world scenario where someone might not have, or two people might have similar friends, would that fill in a null? Or
If somebody does not have a friend in the original table, they just will not show up in the join output. So they basically disappear after the first hop, never to be seen again. If you did a left join here, which is also valid, you could use a left join instead of a join. This is a self left join, then yes, you could get nulls. Well, at least from person to friend, and then probably also, I don't know what would happen after that, but you get a bunch of nulls essentially for that person. So the goal here is understand the base case, the recursive step, and the termination condition. I'm not going to ask you to write a completely fresh recursive SQL query. It is on the homework though, you're asked, it's a bonus problem. So I encourage you to do it and try it and see what happens, just to learn these steps. Yeah?
Would a cycle in the graph affect this curve?
Yes, if there's a cycle in the graph, which we try to eliminate, I believe, with the not in there. It is possible to, that's also why we have to stop early. We might get stuck in a cycle. So we just bail out early. If we do have cycles though, in some cases it could infinitely recurse, but because we're stopping early, the select distinct takes care of that. So we're not gonna keep getting the same person over and over again, the same relationship over and over again. So if somebody's a friend of somebody and they're also a friend of the same person, the select distinct gets rid of that. So any other questions on recursive queries? Okay. Here's another way to do it. Here I'm just using variables that don't clash with the names of the columns, but it's the same situation. It's the same query. So we would get back this result for, I don't remember if this is FOF or FOF. I think it's, so we can use recursive SQL to compute friendships out to any number of hops. But we have to be careful about infinite recursion and loops when we're working with graphs. If we're working with a DAG, which means directed acyclic graph, we're in better shape than we are if we're working with just a regular graph that does have cycles. It's possible to quickly overflow the stack or to get into a case where we ran out of space for the data type or any other thing like that. And we always have to specify a reasonable terminating condition. So we have one last topic here. Are there any more questions about CTEs or recursive SQL? I encourage you to just practice these. They're niche. There's not a whole lot of examples I can give you. They all are going to follow a very similar flavor. So now that we have time, we can talk about processing text and JSON. Now, the relational model typically only likes you to store atomic or primitive types. So char, varchar, int, tiny int, things like that. But over time, data has become a lot more complex. And nowadays, there's cases where we want to store additional data, whether it's binary data or JSON data or text data even. So for analytics, typically you're not going to work too much with text within a database. You may work with JSON though. So there are better systems for working with text. There's MapReduce, there's the document model itself, so MongoDB. There's Lucene, which is a indexer, it's a text indexer basically. And there's Apache Solr, which is a search on top of Lucene. It's a search engine essentially. But MySQL and Postgres do support text operations. So we'll see that in a little bit. And I might have a problem or two on your last homework that does this. So simply speaking, we use this like operator. So if we have a column that contains text, we can simply use like in order to determine whether or not the value in the column is like it's not a regular expression, it's a pattern. So regular expressions are much fancier. This is just a simple pattern. And we specify the pattern as follows. The percent sign is a wildcard that matches 0 or more characters. The underscore matches exactly 1 character. So here's some examples. Let's say I have in a column some text, and I want to match the phrase foobar. I can use the query foo with the percent sign, and this will match foobar. It'll also match foobaz, and anything that starts with foo, basically. Next, if I want to match the word science with anything before and anything after it, I just put a percent sign on either side of science. This will match computer science department, for example, or nutrition science department. The underscores, though, are different. They match a single character. So for example, if I want to match, are we an AM or PM? I specify column like underscore underscore in quotes. So like underscore underscore. This matches exactly 2 characters. It matches AM, it matches PM, it matches ZZ. 2 characters and only 2 characters. It won't match a third character or only 1 character. Then finally, the most complex case is I can match 2 characters followed by anything else. So I must have 2 characters, and then I can have anything else. That anything else can also be no characters at all. So this will match AM, PM, but it'll also match hello. So this is a very simple operator to use, and you'll have some examples of doing this on the homework. So are there any questions about working with text? It seems complicated. It seems like working with text would be very complicated. It's actually not. It's actually very simple in SQL. It's just not efficient. All right. There's a bunch of functions you can use on text. You can concatenate columns or strings. You can read through this at your leisure, but you can take the left or rightmost part of a string. You can convert to uppercase or lowercase. You can even use a regular expression if you want, or return a substring just like you can in any other language. We end at 1:50. Okay, so we have 10 minutes. Great. Working with JSON is equally as simple. JSON is a nested or hierarchical data format that looks like what we have on the screen here. This represents a spec of a TV. This TV has a screen, it has a resolution, and it also has an embedded document within it. Embedded JSON. One's called ports, that specifies the number of ports the TV has. So it has an HDMI port and 3 USB ports. And another one called speakers, which it's a left speaker and a right speaker, both of which are 10 watts, so it's nested. Now, how do we access this nesting? Let's first create a table of products that contains an ID, a name, a brand ID, a category, a JSON, and a JSON blob. If I want to extract how many USB ports a TV has or how many HDMI ports a TV has, I could just do the following. I use the JSON extract function. This is the column I'm going to extract from. And this is basically a path through the JSON tree. It says extract the ports JSON, then under the ports JSON, extract the USB JSON. So ports to USB. Same thing with the HDMI. I can also use this JSON extract in the where clause. So I can only pick out TVs that have a USB port or that have an HDMI port. Now, if I'm looking for a particular screen size, I could just do screen, I think it's like this, screen size greater than blah. You can even combine this with the like operator for text. That's very, very powerful and very easy to use. And it probably addresses 90% of your work in JSON, to be honest. There's also this arrow representation. This is equivalent to, this should be JSON extract. This is equivalent to column, arrow, path. So I guess it's a little easier to read. I don't know. It's easier to type, at least. So any questions on how to extract fields from JSON? It's pretty straightforward. I'll give you an assignment or a problem. I'll try to make it short because you have an exam coming up. Like one problem from each topic or something, each major topic. And yeah, so it'll be either Airbnb data or Yelp data. One of those two is what I usually use. I thought somebody else had an idea of a data set. There's a lot of other functions you can use on JSON. Most of them you're probably never going to use, but you can check the documentation if you're interested. So let's stop there. Hairy lecture. I know these are hairy topics. You have a homework due this Thursday. We're grading your homework from last week. The issue with 5 weeks is just, it's very difficult to get everything graded and done and taught in 5 weeks. So we're going to try to hurry up on the grading, and we'll give you feedback on what you did wrong on homework, on each problem on homework 1 and whatnot. And we'll go from there so you can have access on it for the final. Okay, where is my attempt to? Perfect, I'll come get it. All right, so let's stop there.